I'd like to thank Asher for the kind introduction, and also I'd like to thank Device Technology for the invitation to speak today, and for all the attendees for coming, for a talk that I've entitled Implants Improving Integration, which is going to focus on two technologies that have become available in the last few years, whose goal is to improve interbody fusion. One, nanometallene technology, works at a nano or micro level, and then the other one, Reef Topography, actually acts more at a macro level. And I'll go through these one at a time and talk a little bit about clinical experience. When we talk about why we might do an interbody fusion, there's different rationales for doing so. The first might be for load sharing, which may promote bony fusion through loading of the graft in the anterior column, but also by protecting the screws mechanically by offloading the posterior tension construct. Interbody fusion can aid in deformity correction in spondylolisthesis by releasing the interbody space, or also in scoliosis by helping us level out coronal malalignment. In doing so, you can use it as a fulcrum anteriorly to restore lordosis, and again, in increasing disc height, you can restore foraminal height. And so with this rationale, we can then think, well, what do we want from an interbody fusion device? And so we want something that will match the modulus of bone, that will prevent stress shielding of the graft, but hopefully also limit subsidence by avoiding any mismatch. We want something that's going to encourage bone fusion, something that may be osteoconductive in the future, maybe things that are osteoinductive, and something that's radiolucent, so we can actually assess fusions and outcomes. And so we can then follow on and ask the question, well, how can the materials that we use fulfill these aims? If we look at the early reports of posterior lumbar interbody fusion, they used local bone initially, either spinous process graft or graft harvested from the back of the sacrum, or later, when Cloward described his technique, he used iliac crest bone fashioned into bone plugs that were then driven into the intervertebral space. Later on, manufactured cages started to become popular, and so we had titanium cages, such as the threaded ray cage that you see on the top right here, but also the use of polymers was introduced with the use of the Brantigan cage, which you see in the bottom left. It is a PEEK cage, but with randomly oriented chopped carbon fibers reinforcing it, but it is a polymer, a PEEK cage. So we had titanium and PEEK as these two common materials that we encounter in interbody cages. If we reflect on how those two common materials fulfill those aims that we talked about, if we look at PEEK, we know that PEEK does match the modulus of bone very well. It's radiolucent, so it allows us to assess fusion radiographically. But in and of its own, PEEK is rather biologically inert and doesn't encourage, in fact, it discourages bony growth. Titanium, on the other hand, has a modulus far greater than bone. It's definitely not radiolucent, and radiographic assessment of bone fusion can be quite challenging. But it is bone friendly. It does encourage bony on growth. And so moving on from this, there's been a question, well, can we get the best of both worlds? Can we get those advantages of PEEK and the advantages of titanium together? And the way that that was initially achieved was through titanium coated PEEK. So you're hopefully getting the mechanical and radiological properties of PEEK, but also getting an end plate surface treatment that would encourage bony on growth. There's a few challenges with that. The first is that the PEEK is only applied along a line of sight, so you only get a coating on the superior and inferior surface of the implant. It's not molecularly bonded to the PEEK itself, and so if you're impacting the cages or using an insert and rotate technique, the shear across the applied surface can delaminate that surface. Because it's only on the top and bottom of the implant, it can encourage early bone on growth onto the end plates, but doesn't actually do anything to encourage bony growth through the implant. And so nanometallene is a technology developed by C-Spine that tries to overcome some of those limitations. metallenes, graphenes are very thin layers of materials. Often, like graphene, is down to almost one atom thick layer of carbon. So a metallene is just a thin layer of metal. And nanometallene is the submicron layer of commercially pure titanium that's molecularly bonded to the surface of the peak. And because of the application process, which I'll cover in the next slide, it's able to cover all the surfaces of the implant, not just the superior and inferior surfaces, but also through the void of the implant as well. The bonding process is a proprietary process, so I don't know the exact details, but it's termed atomic fusion deposition that falls under a larger group of technologies called chemical vapor deposition, where you have reactants that react and then deposit the product of the reaction on the surface of the implant. That's done in a vacuum chamber, and as opposed to trying to apply titanium on the surface of the implant, which is a high temperature process, this is done in a vacuum chamber at low temperature, so you don't affect any of the properties of the peak. It's done with high energy, where an electrical current excites the titanium ions, causing a plasma. The reaction occurs and it then deposits the titanium on the surface of the peak. And so you end up with this molecularly bonded layer of titanium all over the surface of the implant, on all the surfaces. But if you cut the implant in half, like the liquid gets into the chalk, you'll just see a little bit of a surface coating, and then the inside is all peak. So it doesn't affect the radiolucency because the product is still predominantly peak. In preclinical testing, this was tested in a sheep cancellous defect model, where a defect is drilled either in the tibia or the femur, and then one of these plugs was driven in. The first plug was made of peak. The second one was made, well, they're all made of peak, but the first one was pure peak. The second one is peak, but the apertures, it's got these holes through it, are actually coated with nanometallene, and there's an interesting result that comes out of that later. And then the third one was purely nanometallene. Sheep were sacrificed at 4 and 8 weeks, and the assessment of bony fusion was done by electron microscopy, micro CT, and histology. And so here we see the histological results of the nanometallene in that defect. This is the surface of that plug driven into the cancellous defect. At 4 weeks with peak, you can see there's no bony on-growth onto peak alone, but with the nanometallene coating, you can see the bony on-growth occurring here. And that's even greater at 8 weeks, where there is some bone starting to form around the peak cage, but it's still separated by the fibrous layer here. When there were those plugs that actually just had nanometallene through the middle, but the surface was peak, you can cut a slice through that implant and you'll get a picture like this, where you'll have a peak surface on this side, and this is the internal surface which had nanometallene on it. And so you can see the distinct difference in the bony fusion here, and that fibrous layer is quite prominent, separating the peak from the bone, whereas you can see the on-growth of the bone opposing the nanometallene surface. This study was done without graft in these plugs, so that's actually bone that's grown through those plugs without any graft there. So truly an osteoconductive and maybe even a little bit of osteoinductive effect of the nanometallene. From a clinical standpoint, and using these in posterior lumbar interbody fusions, I've probably used them over the last 18 months. And I've just picked here up till September last year because I wanted to have 6-month follow-up on these cases. These are in the private sector, not from the public hospital practice, and these are for posterior lumbar interbody fusion surgeries. Most of these were with an implant called Ventura, but more recently I have used the Reef implants, which I'll touch on in the second part of this presentation. Across that time, I've identified 103 implant levels. Now, this is currently these have been assessed by an independent assessor, but I quickly ran through them all in the last week, and just with a basic scoring system of saying 0 was no bone fusion, 1 was bone fusion was occurring but it's not complete, and 2 was there was solid bony fusion. I've gone through and assessed the 6-month CTs. A 6-month CT is my standard practice, and 83 of the implant levels were able to be followed up at that time. One patient had died. Some patients didn't come back for follow-up after their 3-month follow-up, but there wasn't any obvious problems on their 3-month X-ray. On average, their CT was performed at 6 months, but there was a bit of an outlier range there. And so in terms of solid bony fusion across those implant levels, that was identified, my grade 2 fusion was identified in 74 out of the 83 patients. That's about an 89% success rate for interbody fusion. If I just teased out the single level fusions, because that's a more homogeneous group, we had 6-month follow-up on about 38 of them. Again, roughly a 6-month CT scan, and the fusion was present in 95 of them. The 2 that weren't fused had the grade 1 fusion. None of them had this 0 fusion. The 2 0 fusions in this whole series were ones that occurred in a multi-level fusion at the very top level, where at 6 months there was obviously no bony fusion occurring there, and both of them had some loosening of the superior screws. I've just put this image here as an example. It's a L3 to L5 posterior lumbar interbody fusion in a 77-year-old female, and this is her 6-month CT. And we can see here the cage of the voids is obviously the material of the cage. So we can see bony growth through the cage itself, bony growth around the outsides of the cage at both levels. But the arrows indicate that there's some bony growth occurring between the cages. And I don't normally pack any bone graft in that area. I pack the bones in the cages and I pack it around the outside of the cages. And so this is a feature that I have seen on CTs, particularly if I've had to do one early for some reason, is that I've seen the bone actually starting to grow along that surface of the cages. And so again, it's like in that sheep Cancell's defect model, that you have a material that is actually osteoconductive. In the absence of direct graft there, it's actually the bone is growing along that surface. This is just a second example of the same thing happening. This is an L3-4. That was an L3-4 fusion here, where the gentleman had a significant collapse of the L3-4 disc space on the left-hand side. This is a 6-month CT scan, and not only is there bone growth through the cage and outside the cage, we can also see bone growth occurring between the cages as well. So in terms of just taking nanometallene as a group, it seems to have on this preliminary assessment a fairly high rate of fusion success. And these are fairly impressive images, I feel, from my previous experience of 6-month fusion. Nanometallene works, I said, at a microscopic or nano scale, but Reef Topography is a new technology available in some interbody implants from C-spine and device that's really been available only in the last 12 months or so. And Reef Topography describes a macro structure to encourage bone fusion. This is the Ventura cage that's a nanometallene implant that I said formed most of that previous series. And like most interbody implants, it has anti-migration teeth on the surface here that are designed to provide some back out resistance on implantation. The Reef Topography actually modifies that those superior ridges and actually undercuts them. So we might call it an undercut macrostructure. It almost looks here like a wave crashing on the shore. So it's on the surface of the cage, rather than just simple anti-migration teeth, there is this undercut macrostructure. But then also on the inside of the implant, you will see that there are these slots cut in the side, inside the cage. So there's also an undercut macrostructure to the interior of the cage as well. The rationale behind this is firstly that if you have undercut macrostructures, you're going to have more nanometallene surface available for bony on growth. Wedge teeth by themselves will actually increase the surface compared to a flat surface, but if you have an undercut surface, you'll have even more surface area. But once bone grows in and underneath that undercut structure, you actually get much better bony interlocking, and you can pack graft across the surface of the implant, so you'll get more graft material in direct contact with the end plates, and it has been demonstrated to increase mechanical stability, which I'll come to in the preclinical assessment in a moment. If we think about that undercut macrostructure, this is what I was talking about, is that if we have bony ingrowth into an undercut macrostructure and you then try and distract the implant from the bone, there's going to be an increased resistance to pulling out, as opposed to if you just have anti-migration teeth and you pull them out. So it's able to lock the cage in. But then also the bone is loaded not only under compression, but also under tension, so you're actually getting increased bone loading, graft loading, and hopefully then increased bone fusion rates. In preclinical assessment, an interbody sheet fusion model was used, and it was L45 in the sheet with autologous iliac crest bone graft. The control implant is illustrated here, that doesn't have any, just has a flat surface with the iliac crest in the middle, and then the Reef topography cage had the undercut macro structure, both on the surface and on the inside. The time points for assessment were at 6 and 12 weeks with micro CT, biomechanical tensile testing, and histological assessment. In terms of the micro CT, this is a micro CT here of one of the Reef cages, and you can see the ingrowth both into the actual macrostructures on the surface of the cage, but also into those undercut macrostructures on the internal void of the cage. So it does perform as expected, and that's confirmed on histology. When you do attempt to distract those two vertebrae, at 6 weeks and 12 weeks, the cages that had the levels that had a Reef topography cage had an up to 3 times increased load to failure compared to the normal cages. And so not only are you seeing it both radiologically and histologically, the results of the cage, but also in terms of mechanical testing, you're seeing very early increased tensile strength in those cases. From a clinical fusion outcome standpoint, I don't really have sufficient numbers to tease that out of that previous series, largely because I've only been using them. The pandemic confuses me a bit in terms of timing, but I think it's only been over the last 12 months, and I don't have a sufficient number to really look at 6-month follow-up for those. So hopefully I'll be able to present that at some later time. So really over the last 20 minutes, I hope to have presented to you my personal experience and a bit of the background behind these two technologies available from a C-spine and device. The Nanometallene technology, which is a surface coating that works at a microscopic or nano level, as well as the Reef topography that actually then is a macro structural alteration to the design of the cage that works at that macro level. So both at the micro and macro level, hopefully they are helping implants improve bony integration.
Thanks, Dr. Ball. Thanks for sharing your experience, for shedding some light on how those, first of all, how those technologies are actually integrated into the device, and then secondly, some of the clinical outcomes and your observations on how they've integrated into your practice and potentially helped some of your patients as well. We have got some questions that have come through, so we'll start with a couple there for Dr. Ball, if that's all right. So got one. Thanks, Jonathan. What is the bone graft substrate that you are utilising with the Nanometallene and Reef interbodies?
Can you see that up on the screen?
Yep.
Yep, I just quickly ran a query for Mark because I saw that question coming up. So I've just asked it to count the different bone grafts here. In the early stage of that series, at the end of 2019, BMP was still in use in Australia. So there were 31 of the cases that had BMP. But since then, I've been using the Boost fibers from a device, but also from Oz Biotech, sometimes some Fiber Crunch, which are both essentially demineralized bone products. This is together with local autograft. And there's been a handful of cases where I've used I-factor in there. Maybe interestingly, in a subject of talk for a different time, it's small numbers, but if you compare the fusion outcomes in the 31 BMP cases versus the Boost and other demineralized fiber cases, there's not really a significant difference in the fusion rates between those, but I haven't really teased that out. I just quickly ran that query on the spreadsheet then. I hope that helps, Mark. I'm not sure if there's a follow-up from that.
So another question for you, Dr. Ball. Have you noticed any change in the subsidence rates since your adoption of nanometallene and Reef compared to either just straight peak or 3D printed titanium?
Yeah. So I think one of the issues there in that is it's not something I've measured specifically. And when I went through a phase of using 3D printed titanium cages, I felt there was more subsidence, but that's a feeling and not something that I can back up with any objective measure. And because a titanium cage is in your face on an X-ray, you do, I think, notice subsidence more than you maybe do with peak, because in peak, you're looking at a few little white dots. And so I can't necessarily say that I've seen greater subsidence in this situation. I feel it may be less, but I don't have data with which I could back that claim up. It might be something more to look at.
Great, thank you. And then I suppose following on from that comparison with porous TI cages as well, how does the boning interlocking from a Reef topography cage compare with porous TI cages in your opinion, I suppose?
So in terms of, I'm not sure if that question's asking about do I clinically feel a difference when I first put it in?
More at the 3 and 6 month points for bone integration with the cage.
I think I said I haven't actually specifically looked at those, and I don't think the numbers are necessarily that great. Actually, yeah, I'd have to dig into that to look at the difference between Ventura versus Reef and see whether there's, how much additional benefit there is in nanometallene alone versus nanometallene together with Reef technology.
Sure. Cool. Well, thank you, Dr. Ball. Awesome. Well, I think we're kind of coming to the end there. Unless there's any more questions that come through on the chat line in the next minute or so, I just wanted to take the time to thank you for preparing for the talk this morning, for sharing your experience. Jonathan, it's always a bit of bearing your soul when you put your own patient series up. So thank you for leaning into that as well. And yeah, just thanks very much for jumping on and being part of the morning. I don't think we have anything else through on the text line now, so we might wrap up a couple of minutes early.
Thanks everyone for attending.